the idea, yeah, is knowing what is the distribution of the complex amplitude in this plane, which corresponds here with a focal point, yeah. So, but it just corresponds to the pupil plane. I would like to know, yeah, what is the resulting distribution of the complex amplitude in the focal plane, yeah. Now, would you agree that, well, at the point M, I may represent, yeah, the field of radiation, yeah, in the following way? I can say, okay, the field of radiation, yeah, is a complex amplitude, and since it is monochromatic, I know that it oscillates with the frequency nu. So, yeah. Now the complex amplitude, yeah, I may rewrite it as follows. Well, it is equal, yeah, to, well, a real amplitude. Now multiply. This is a complex phase, yeah. And now I multiply it still by what I call the pupil function. Yeah, so the pupil function is equal to 1 if I'm inside the pupil, and it is equal to 0 if I'm outside the pupil. Yeah, so very, very, very easy. Now, while following the principle of Huygens Fresnel, yeah, I may, and well, simple laws of geometric optics, I can say that, well, at this focal point here, in the focal plane, all the rays, yeah, which are converging, yeah, to that point, yeah, come before the optical lens system, yeah. So before, on the left side, yeah, they all come parallel, yeah, to this ray, because this ray, yeah, goes from H prime to N, and so come from a parallel direction here, and all those rays which will converge at N, yeah, are parallel, yeah, to this direction, yeah. So I have represented there. Would you agree with that, or is there any difficulty? So I just show it for a very thin lens, yeah. So here is the focal plane, and if this defines, yeah, the point that I've named N, with the coordinates x prime, y prime, I say the following. Let's assume, so this is the focal plane, of course, yeah. Well, I know that this ray, for the case of a simple lens, yeah, is not deviated, yeah, because it goes through the center O. Here it's a bit more complex because the lens is more complex, and you have to refer to the two principal points, H prime and H. So this rays goes through H and remain parallel. And now I may say, okay, well, if I would define here the pupil plane like that, yeah, necessarily, yeah, from a point M, the ray which goes here is parallel to this one, goes like that. Well, from another point, it would be still parallel, yeah, and goes to here, because I know that the parallel beam, yeah, converge, yeah, into N. So very simple. Okay, so I may say now that at the point N, the contribution, yeah, coming from the point M and from a small surface area dx dy in the pupil plane will be what? Well, it will be AXY multiplied by exponential of plus I2P nu t, and multiplied by this factor exponential I phi x, where this accounts for, well, a phase retardation. Now I take the convention, yeah, so it's just a matter of convention, that the ray passing via O, okay, has a phase shift, so f for x equals 0, y equals 0, is equal to 0. So I take this as a reference, yeah? So, okay, But at the point M, this will not be equal to 0. Yeah. So how shall I find what is the phase shift between the ray coming from M and the ray coming from O? Well, it's very easy. Yeah. I take the projection of M along this direction. Yeah. So the projection of M is a point K. Yeah. So it means that the blue line that you see belongs to the same wavefront. Okay. So the points M and K oscillate in phase. Yeah. So the phase retardation between M and O, well, is just due to this path difference. Yeah. Okay. Now I shall try to find out what is the value of this path difference. So I may say, okay, the phase xy is equal to 2 pi divided by lambda multiplied by delta, where delta is equal to the difference between the distance, so I write it like that, distance min minus the distance between O j n. So this is the path difference between the two rays, yeah. So it's the difference between the distance, yeah, of the ray going from M passing via I and going to N and the other one, yeah. So the diagram will come again. How to evaluate, this path difference? Well, I just need to make the scalar product of the vector OM multiplied by the unit vector along this direction. So I suppose that U has been normalized. And if you project OM on that direction, you will find exactly what's the length of the path. Yeah. Now to make this scalar product, I know that the coordinates of OM are the following. I have a coordinate x, y, and 0. Yeah, because I adopt this system of coordinate x, y, and z. Yeah. So the coordinates of M is in the plane x is in the plane z equals 0. Yeah. So it's x, y, 0. Now the coordinates of the vector u, which is a unit vector, is easy to deduce from the fact that this direction is parallel to that one, Now, what is the distance between h prime and f prime? It's f, it's the focal length, Now, the coordinates of these points, are therefore, x prime, y prime, f, okay? And now, what I do, I divide everything by f, so I have x divided by f, x prime divided by f, y prime divided by f, and f divided by f, it's 1. Now, I assume that the focal length is significantly longer than the module of x prime and y prime. It means that when I take the modulus of this vector, what I find that the module of u is equal to the square root of x prime over f square plus y prime over f square plus 1. Now, these are second order terms, because f is much bigger than x prime and bigger than y prime. So it goes away. And to first order, I may say, well, this is a unit vector. Okay? Now to make the scalar product of the two vectors, well, it's easy. I'm just co-adding the product of all those coordinates. So it will be equal to x times x prime divided by f plus y times y prime divided by f plus 0 times 1. So this is the result of the scalar product. So I may write here that the phase difference between the ray going from M to I j n and O j n is equal to 2 pi divided by lambda times delta. But this length is longer than the other one, So delta is a negative number. So I say, okay, minus 2 pi over lambda multiplied by x prime over f plus y prime divided by f. Okay? So finally, I find that the contribution to the amplitude of the electric field here due to the point n is equal to, well, it's a xy multiplied by exponentiation of minus 2 pi multiplied by x prime on lambda f plus y prime over lambda f multiplied by exponential of I2 pi nu t. So the contribution to the amplitude, if it's due to a small surface element dx dy, well, I still have to multiply it by dx dy. Now, this I can take away and say, well, this is the contribution to the amplitude at the point n. And now, well, do you agree that here at the point n, I receive contribution from all the points in the pupil plane? So I have to integrate over all the points m in the pupil plane. So I integrate. This is what I obtain. So I obtain that, okay, the amplitude at the point n is equal to this quantity, which depend on the x prime over lambda f and y prime over lambda f. These are the only parameters appearing in this expression. Otherwise, I integrate over the variable x and y. So now I set the change of variables p equal x prime over lambda f and q equal y prime over lambda f, and this expression becomes the resulting amplitude of the electric field in the focal plane is equal to the double integration of xy, then exponentiation of minus 2 pi multiplied by px plus qy dx dy. And here I see that it's in a two-dimensional space of Fourier transform. So APQ, the distribution of complex amplitude in the focal plane, is equal to the Fourier transform of the distribution of complex amplitude in the pupil plane as a function of the new defined coordinates p and q. So these are not x prime and y prime, but they are defined within a multiplicative factor. The multiplicative factor being 1 over lambda f, 1 over lambda f. And this is the fundamental theorem. And a very nice result. Very, very simple. So I remind you that the other important theorem that we established was the following one, was that the visibility of the fringes, so it's something different, is equal to the module of the complex degree of mutual coherence. So it was 0 UV. And this was also equal to the module of a Fourier transform of the distribution of the normalized intensity at the surface of celestial objects, UV and module. So I see, wow, the operations that we will perform, in this case, are very similar to what we have already been doing, So Fourier transform, Fourier transform is recipes. So any question, on the establishment of this very important theorem, because you will see it's a very powerful theorem, leading to extremely interesting results. So the demonstration, will be in the lecture notes. First application, let's assume that we have a XYZ, that we have a square aperture as an entrance pupil, of a converging system, So it means that we have a mirror, which has a square size, or a lens, which has a square size, shape, And so let's assume that this side is small a, and this side is also small a. And I'm looking, at the zenith, at a very distant star. So, in the absence of atmospheric perturbations, this star emits plane wavefronts, And so the plane wavefronts arrive here, and after touch the pupil, and because the pupil, is a space coherent, I may assume that the distribution of a complex amplitude, in this case, is a constant, Well, I can say, okay, the distribution of the complex amplitude in the pupil plane is a constant, and it is A0, It's a real value, Now, let's apply this theorem. What is the distribution of the complex amplitude in the focal plane, of an instrument, a telescope, which has a square shape? Well, it's the Fourier transform of A0 as a function of PQ. Okay, but A0, A0, can just go away, from the Fourier transform. And here, what should I write? Well, the square aperture, is the Dor function of x over a multiplied by the Dor function of y over a. Now we have seen already before that this can be shown to be equal to the Fourier transform of the Dor function xa, which depends on variable p, because I have separation of variables, multiplied by the Fourier transform of the Dor function of y over a, which now depends on the variable q. This one, you remember, we applied the similarity property, and we found that, it was equal to a multiplied by the Fourier transform, of the Dor function, but which depends on the variable a times p. So it will be the sinc, so the sign cardinal of pi of AP, a times p, like that, times a, the same, times the sign cardinal of a times q. You agree? So it's equal to a square times, so it is a sine of pi AP divided by pi AP multiplied by sine of pi AQ divided by pi AQ. Now we know that when we are making observations, what we are measuring is not the amplitude, but we are measuring the intensity distribution in the focal plane. So the intensity distribution in the focal plane, you remember, is equal to, in fact, the amplitude times its complex conjugate. But in this case, everything is real, So easy, it's equal to a PQ to the power 2. So it will be equal to a to the power 4 times the sine of pi AP divided by pi AP square times the sine of pi AQ divided by pi AQ square. And now I think I have a picture to show this result. It's here, yeah? So we see here, this is a square aperture and a wavefront, yeah, falling onto it, yeah? And now this is the result, yeah, showing, oh yeah, I forgot to, if it was A0, yeah, here I forgot the A0, A0, now the A0 square here, n times the A0 square here, and A0 square is what I call I0, yeah? Now, this is very interesting to see, yeah, that the intensity, yeah, the maximum intensity is obtained for P equals 0, Q equals 0, yeah? Because sine x over x, yeah, the module is equal to 1. So the maximum amplitude is a to the 4, yeah? Now, well, it seems surprising because, you know, the surface, yeah, of the pupil is a over square, yeah? And here we see a dependence of a over the power 4. Does anyone know why? Well, we will see it in a moment, yeah? Now, you see that we have this nice shape, sine cardinal, and then we have secondary maxima, yeah? And we will see in a moment, yeah? We'll make the same application, yeah, for the case of a circular aperture, so a mirror, which is circular symmetric, yeah? And well, it's something very similar, yeah? So it's what I said, yeah? When you do calculations, yeah, about Fourier optics, it's very nice to take square aperture, square stars, you know, and because the results are very simple, they are more complex, yeah, for the case of a circular symmetry, yeah? Okay, now what I would like, well, the angular resolution, yeah, of such a mirror, yeah, is determined, yeah, by the width, yeah, of this first peak. You agree? So the width, yeah, is the distance between the two minima on both sides, yeah. So it's a distance between this point and that point. So let's try to find out what is this angular size. So do you agree that the sine will be equal to 0 if pi times a times p is equal to pi? Yeah? Because the sine, yeah, if this is equal to pi, well, this is 0, yeah? So it will be, it will correspond to this minimum here. And if it is a minus pi, it will be here. So, okay, what I can write is that I will have 0 whenever this is equal to plus or minus pi. So I may divide by pi, and I find that in that case, p will be equal to plus or minus 1 over a. Yeah? Now p, I remind you that p is equal to x prime divided by lambda f. So here I could write, yeah, that delta p, so the width, yeah, of the peak is equal to 2 over a. Yeah? Yeah, because 1 over a minus 1 over a, it's 2 over a. So from this relation, I find that delta p is equal to delta x prime divided by f times 1 over lambda, and this is equal to 2 over a. Now I concentrate here on this result, and I may rewrite it in a different way. Delta x prime over f is equal to 2 lambda over a, and this I may call it, yeah, the angular resolution of the mirror. Yeah, why? Delta x prime, yeah, is a separation between the two minima that I see from the center of the lens, because at a distance f, yeah, the distance of the focal length. So it's an angle, yeah. It's angular resolution, yeah, of your mirror. So you see that the angular resolution of a mirror here, it's 2 lambda over a, where a, yeah, is a side of the square. So smaller is the wavelength, better is angular resolution. Larger is the size of the mirror, better is angular resolution. Any question on this? Yes.
Sir, you know that from Rayleigh's criteria of resolution, that first minima of one star should follow the central illumination of the second star.
Yeah.
In that case, that central illumination, center is UV00, and first minima is the resolution.
Okay, yeah, sure.
And it's just twice of that.
Yeah, sure. It's just a matter of convention to know what you are speaking about, yeah? So in this case, yeah, I decide to take the width between the two first minima, yeah? But I agree that if we follow your criterion, yeah, it would be a different value. But I will adopt the same criteria when referring to a circular aperture, and then we will see what's the difference, yeah? But I agree with you, yeah, sure. Okay, now, well, second application, yeah? Well, maybe not second application. I still stay here, xy. So I still have the square aperture, like that, yeah? And now I assume, yeah, that I'm not looking at the star anymore in that direction, but in this direction. Okay? And now we could wonder, yeah, well, what happens, yeah, to the image that will be formed in the focal plane, yeah? Well, do you agree that in that case, the main difference is the following, yeah, is that the plane wave, which will hit the pupil plane, yeah, will be slightly tilted, something like that, yeah? Which means that if here I have a zero phase difference, yeah, well, here I will have a positive delay, and here I will have a negative delay, yeah? Okay? So how to do that, yeah? So it is an interesting case. Well, I would like to go back to previous view of the optical converging lens here, yeah? Okay. So let's assume, yeah, so this is important, yeah, that I'm observing, yeah, well, a star in that direction. Yeah, okay, in that direction, yeah. So the plane wave, yeah, will be perpendicular to the vector u, yeah. Okay. And now what I see, and I don't know if it's clear, but so I have here the pupil plane. So the pupil plane is represented something like that. Now here I have the point O. Okay, so let's assume that I'm observing the star in that direction. Now I decide that the vector unit, yeah, which is along that direction has the following coordinates. I would say, okay, B over F, C over F, and now here 1. Now in the focal plane, I will go here to a point which coordinates, yeah, are x prime equal b, c prime equal c, and of course the z prime, yeah, the z prime is the focal length, yeah, yeah. So indeed, yeah, it is a unit vector pointing in the direction of the star. Now the plane wave, I don't know if I will be able to properly represent it, because now it will be tilted. So the plane wave would be something like, yeah, something like that. I'm exaggerating a little bit, yeah, but just to see something like that. Yeah. Now, if the point M xy is here, what I see, yeah, is that here the phase difference will be 0, but here the plane wave, yeah, will take this additional path, yeah, to reach M, yeah. So now it will not be yes.
aperture?
Excuse me?
Plane of the aperture?
Yes. Yes. So this is the pupil plane is a plane of the aperture, and what I represented in blue, yeah, is a plane wave coming from the star. Yeah. So I see that there will be a delay, yeah, and so the delay is before, yeah. We found that delta was equal previously, yeah, to it was x prime over f plus y prime over f with a minus sign. Now it's an opposite sign, so it will be plus. And now I replace x prime and y prime by b and c. So it will be b times x over f plus c times y over f. So this is very easy, yeah, to find out. You need to concentrate, yeah, at home, yeah, and do the exercise yourself. You will see that this is the expression, yeah. So in that case, yeah, how should I change the expression, yeah, of the Fourier transform? Well, it will be something like that. It will be APQ is equal double integration, yeah, of A0 times exponentiation of I to pi multiplied by b times x over f plus c times y over f. And now Fourier transform exponentiation, yeah, of minus I to pi of x prime over lambda f plus y prime over lambda f. Okay, and here I've forgotten, so it's 2 pi over lambda, yeah? So here I write over lambda over lambda. So this accounts, yeah, for the phase retardation, yeah, of the plane wave when it hits the point xy. Yeah, because, well, the star is not anymore, yeah, at the zenith, so the plane wave does not coincide with the pupil plane, but it's tilted, yeah. So it's just geometrical, yeah. Okay, then dx dy. So this would be equal to A0 times double integration of, I rewrite the things as follows, minus I to pi multiplied by, here there will be x multiplied by p, then minus b over f lambda plus y multiplied by q minus c over f lambda dx dy. Okay? And this, I find that, oh, this is just A0 times the Fourier transform of, well, the square aperture as before, yeah, as before. Yeah, because, well, I forgot to insert here pi x over a times pi y over a. So here also I insert it, yeah. So it's a Fourier transform, yeah, of x over a times y over a, not for the variable p and q, but for the variable p minus b over lambda f, and for the variable q minus c over lambda f, like that. So what I find is exactly the same result as before, yeah? But instead, yeah, of being centered at the value p equals 0, q equals 0, it has been translated, yeah, as the value p equal b over lambda f and q equal c over lambda f, yeah? Now, well, if I write, yeah, p equal b over lambda f, it's also writing that x prime over lambda f is equal to b over lambda f, which implies that x prime will be equal to B, and that y prime will be equal to C. Yeah, and it's exactly what I was expecting to get. Yeah, yeah. So if you're observing with a square aperture, yeah, a star, which is not at the zenith, yeah, what you will see in the focal plane, yeah, is still the point spread function, the response function of your square aperture, yeah, but translated. So there is invariance, yeah, of the PSF in the field of view. So this is a demonstration, yeah, if you have a perfect optical system, there is invariant, there should be invariance of the point spread function in the field of view. Now if you have geometric aberrations or, you know, optical complication, it will not be always the case, yeah, but this is the result, yeah, so interesting. So the answer is that, well, this, instead of being here at P equals 0, Q equals 0, will simply be translated. Yeah. So we still obtain the same result. This is the problem of interest, yeah, to us, yeah, is that, well, most of the telescopes, yeah, do not consist of a square mirror, but a circular aperture, yeah, or spherical, well, spherically symmetric lens, not spherically, but a circular symmetric lens. And so now you see the aperture is represented by this model. And what we will establish, you will see, it will go very fast, yeah, because I will base the results, yeah, on the demonstration we did last time concerning the Fourier transform of a stellar disk, which is circular symmetric. So because it's exactly the same, yeah, yeah. And what we see is the results, this is interesting, yeah, is that in the focal plane we should observe an airy disk, yeah, an airy disk. So how to establish that result, yeah, based upon the demonstrations that we did yesterday. The reminder, yesterday, yeah, we established that the visibility, which is the module of the complex degree of mutual coherence, for the case, yeah, of, well, a star which was represented by a circular disk with a radius, yeah, you remember, rho, uniform disk, UD, like that. We found that it was equal to, well, the Fourier transform, yeah, of the distribution of the complex degree of mutual coherence, yeah. So it was the module, yeah, of the Fourier transform of the normalized intensity I prime zeta theta as a function of, well, we found the only parameter was R over lambda, like that. And we found the result, yeah, that it was equal to the module of 2 times the first order Bessel function, yeah. Then it was 2 pi multiplied by rho of UD times R divided by lambda, everything divided by 2 pi rho UD R over lambda. So, yeah, so this was what we found, yeah. Now you remember we were using here, yeah, the normalized intensity distribution at the surface of the star, yeah, which was, 1 over pi times the square of the angular radius. Now the problem, yeah, we should solve now is to find what is the distribution of the complex amplitude in the focal plane, yeah. And we know that, well, it's equal to the module, yeah. So Fourier transform here, the module of the Fourier transform. So of what? Of the distribution of the complex amplitude in the pupil plane, yeah. But what I would like to do, yeah, I know that it is constant, that it is circular symmetric, but I should normalize it, yeah? Now, if I normalize it, yeah, I should divide, you agree, by the surface of the aperture, yeah? So I should divide by pi r square. So, okay, let's assume that I've divided by pi r square. Now here, the coordinates I expect, yeah, would be something, so P, it's x prime over lambda f, so P equal x prime over lambda f, Q, it's y prime over lambda f. So I expect, you know, that this will correspond to something like small r divided by lambda f, r prime, where r prime, yeah, is a radial distance in the focal plane. Yep. So okay, I have right here, it will depend now on r prime over lambda f, like this. Now I multiply, this is important, by pi r square. Yeah. Because, yeah, here I've normalized it, yeah? So here I denormalize it, okay? So what shall I find? Well, that it's equal to pi r square multiplied by what? By something similar to that, yeah? So it will be twice the value of the first order Bessel function of 2 pi is 2 pi. Rho ud. What shall I set for rho ud? Here. What?
Smaller.
Well, no, I will put a big R, which is the radius of the mirror. Yeah? This was the angular radius of the star, so this is the radius of the mirror. Okay? Now the R over lambda should be R prime over lambda f. So I write R prime over lambda f. Like that. And then I divide by the same quantity, 2 pi r times r prime over lambda f. And I take the module. See? You agree with that or not? Well, it's just, you know, you have to find the corresponding change of variables, yeah, but it's trivial. One has to concentrate, and it's not difficult, yeah. Okay, now, well, IPQ, the intensity, yeah, well, only depends on r prime, in fact, yeah. So the intensity as a function of r prime is equal to what? Well, I have to take the square of that expression, yeah. So it will be pi times r square at the power 2 multiplied by 2 times the first order Bessel function times 2 pi r times r prime over lambda f, yep, divided by 2 pi r prime over lambda f. Take the module, no, I take square, yeah. And in principle, yeah, this should be the illustration of that quantity that you see here, yeah. Now, well, let's see if it makes sense, yeah. You remember that the first order Bessel function will have a 0 for the value of the argument equal to 3.8, yeah. So here I just write, okay, 2 pi times r prime over lambda f should be equal to 3.8. Okay, I divide by pi, 3.14. Well, 2 times r is a diameter, yeah? So I divide by the diameter, okay? And now I multiply by the wavelengths. So I find that r prime over f is equal to 3.8 divided by 3.14, it is 1.22. So 1.22 lambda over d. Now the distance between the two minima, yeah, will be twice that value, yeah, okay? So I have to multiply this by 2. and this by 2. And I find now that, well, the angular resolution, yeah, of a circular symmetric disk is equal to 2 times r prime over f, which is equal to 2.44 lambda over d. Yeah. So the width, yeah, the basis, yeah, of this peak, yeah, is 2.44 lambda over d. Before, yeah, what we were finding, you remember, for the square aperture, we were finding that the angular resolution of a mirror, which is square and which has a size of small a, is equal to 2 times lambda over d. Over a. Yeah, it was a was the side, yeah, of the mirror. And now there is an interesting philosophical question. Yeah, if I give you, yeah, a square aperture, and if I give you a circular aperture, which area are the same? Yes, so the surface are the same. Which one is the most resolving? What would you select? The square one or the circular one? Well, to find out, yeah, you have to do the small calculation at home, yeah? So you assume that pi times r square is equal to a square. So the two pupils have the same surface, and then you try to find out which one is the most resolving, yeah? I know the answer, yeah, but I keep it secret till tomorrow. Who among you, yeah, already made that demonstration, yeah, well, so roughly with the first order Bessel function to find the expression of the airy disk, yeah? Because very often, yeah, at high school or even in the university, yeah, the professor of optics, yeah, tells you, well, this is the airy disk, yeah, this is the expression, yeah. Did you see the demonstration before or not? No. But you see, it's very simple, yeah, it's just Fourier optics, yeah, just Fourier transform, yeah. And the complication is that when you use square or rectangular aperture, everything is simple, it's sinc function. When you use a circular symmetry, whoa, zero order, first order Bessel functions, yeah? But it's okay.